Okay, let's get started. So it's a real honor to introduce Jim Keller. For those who do not know Jim, so there are probably handful of people in the world who knows how to design high-end processor and make them commercially successful. And Jim has done it many times. So he's one of the celebrated ones among those small set of people in the world. And just to give you some examples, if you think about in the Zen architecture, which essentially turned that company around from say maybe $5-10 billion company to a $115 billion company.
1.5 billion. It's worth 1.5.
What 1.5 to 150? So okay, I was that's 100 times, right? So if you look at that, 100 times. So if you look at that, you'll find that for most part it was related to the success of Zen architecture, and thanks to Jim. And he has not done it only once. If you look at Apple's A4, A5, A6, A7, many of those codes like has Jim's fingerprint onto that. Also, if you think about x86 64 instruction set, which Intel or AMD processors use, Jim has played a key part into that. So I might not be aware, but Jim has played a part in your life in some way or other through his work. And today he's here in the capacity as the CTO of Tensor. And if you want to hear about how the compute going to look in future, this is better than Jim to get us out of that. So that's what you think. Great.
Yeah, great, thanks. It's good to be here. I had two important talks to do this week. One with you guys, and the other with the Prime Minister on Friday. So I came here first. Is that a good sign? Yeah. And it's just friendly. So any questions you have as we go along, please just shout out. We'll talk. I like to interact with people. Is this whiteboard blue and turn? I wanted to use it. It looks like it's on. Oh, look at that. That's pretty cool. So, because I have whiteboard technology here. Blackboards are old school. You can't. All right. I was told this was a tech talk. You guys want to hear about computers stuff? I'm in the right place. Because with the Prime Minister, they told me that I'm going to explain how India is going to lead the world in chip technology, and which will be good. I don't know how to do that yet, but I have until Friday to make that talk, so it'll be really fun. And if you guys have any ideas, just let me know, because I'll put them in the talk. And then if it goes online, you can see. Maybe that's what we should do. We need like 3 ideas from you guys that I'll put in the talk on Friday, which I think like 8 or 5 people are going to watch or something. It'll be all right. So here's what I thought I'd do. I do a little bit of a history lesson. As he pointed out, I'm really old, and I've been working on computers for 40 years. And then I wanted to talk about abstraction layers, because we've been thinking, so we're building an AI processor and a new RISC-V processor. And the reason we can build those successfully is because we have a design methodology that breaks the problem into pieces. And I'm going to basically have a little story about how we take that methodology and apply it to hard problems. And what I've seen is if you do that kind of thing properly, you can succeed, and if you don't, you'll fail. And so I want to talk about that, and then I'll talk a little bit about let's say the future of AI, which I think is really interesting. And it's actually more interesting than people think, which is kind of crazy because they already think it's interesting. So I'm going to talk a little bit about IT, SoCs, the CPU, AI software, AI hardware, and then I have a picture of the cloud we're building, because Ken Torrance is a super hands-on company, and we're basically building everything ourselves. And the reason we're doing that is because you learn a lot more that way. We leverage open source, but everything we do ourselves, we learn a lot from. All right. So that's a picture of the VAX 8800. I worked on that starting in 1982. That's 40 years ago. That computer is there's probably a computer in here that's faster. We used to sell that for $500,000. It took 150 people 4 or 5 years to build it. And here's the funny thing. It ran assembly language and C programs, right? What it did. Way back when. Does anybody here use Emacs? Does anybody know what C programs are? A couple. I still use Emacs. It's crazy. But I use the same text editor and I write C programs. And to be honest, they look a lot like that. And as you know, when you write a program like ABC, integer, floating point, maybe struct, maybe you have dynamic allocation, and then you write declarative sentences, right? If this is bigger than this, then do this, A plus B, right? And I've described computer programs actually look a little like how you think. Like you think, that little voice in your head thinks in kind of this straight line, right? And you know, it says do this and this and this. Right? And that's how in computers then execute those statements in that order. Now underneath that little thought in your head, by the way, is 10 billion neurons firing at something like 10 to the 20th operations a second. And there's nothing in your brain that looks anything like a serial narrative, but for whatever reason, that's how it works. And computer programs work that way. And then I really like this graph. So Gordon Bell was the CTO of Digital Equipment. I think on my, I was there for 2 weeks and I met him. I didn't know who he was. And he came and he told me about hierarchical design and structured design. We had this new CAD system and I argued with him for an hour. I didn't know any better. And then somebody said, that's Gordon Bell. He's the CTO of Digital, right? And he was a great guy. The best I could tell, when Gordon Bell was at Digital, the company went up and when he left, it was down. That's my first experience with a computer great who actually set the direction of that company. But Bell's law said we went from mainframe to mini computers to workstations to PCs to phones. And every 10 years or so, you have enough more transistors to build a faster, better, or smaller computer, right? And that makes sense. And I used to look at this graph and think, these computers are so different, right? Mainframe, you know, mini computer, workstation, you know, PC. Actually.
Until next time.
This computer's talking to me. It's not very smart yet, but it will be. These computers actually are running the same programs, right? And then over time, we've developed things like JavaScript, HTML, higher level languages, but they basically compile down into a glorified C program and then into assembly, and they run the same instructions. Over the last 40 or 50 years, we've made computers way faster, way smaller, but they actually run C. Does that make sense? And I'll get why that's super important in a minute. And the thing that made this happen was this is the Moore's Law curve. And some of you may know, I gave some talks about Moore's Law. It's not dead because, well, when I was at Intel, it's the Moore's Law company, and people said Moore's Law is dead, but basically when Intel was dead. I think that's A, be a bad thing to be. It's actually materially wrong. Like this curve, it wiggles around a little bit about how many transistors we can put in a chip every year, but it's still moving along pretty good. And my friend Pushkar around the day pointed out that the Apple M1 Ultra is right on the line for transistors in the computer. So now the thing for computer designers, if you guys have taken architecture, yes. Yeah, please do.
So do you think it remain economically viable? What's that? Would it remain economically viable to put more, smaller technology and so on?
Yeah,
it's technologically possible, economically possible.
I'll give two answers. But I realize that there's a funny equation. How much time do we have, by the way? So I might, we have as much time as we want. People stay for an hour.
Yeah, yeah, yeah.
You know, when you shake your head like this as an American, I don't know. So just maybe for 1 hour. This is BS. This is. I'm getting used to it. I've been in India before, so I can almost understand it enough. So I've heard so many times that the next generation technology is more expensive, and we're not going to have a crossover, right? We'll see if this whiteboard works. That was a good idea. Right? And typically what happens with the new technology, there's a curve that says over time that it gets cheaper. Right? And then a new technology comes out and it's more expensive, but then it crosses over. Right? So they calculate the crossover point. And then periodically Intel or TSMC will say the new technology doesn't cross over, but that so far has never happened. Okay? Does that make sense? But here's a really funny thing. Oh, it's the same curve. All right, imagine this is wavelength. This is energy. Right? So as we make things smaller, we use shorter wavelengths of light to do it. And unfortunately, wavelengths of light, if you make the wavelength smaller, the energy per photon goes up. So this is the E versus lambda curve. And we're there. EUV. Right? It takes a megawatt of electricity to make a milliwatt of EUV to right on it. Yeah. Right? That's not a very good ratio. When you have a light bulb, like incandescent light bulb is 20%, takes a watt to make it. And that's the photons get more energetic, they start to move the atoms that they're trying to pattern. Well, there is a funny limit. And we'll see what to do about that. But I didn't know that when I was at Intel. So, but now I do. But on the other hand, biology is really good at placing atoms. And there's a whole bunch of tricks for how to place atoms. And I don't think we've even started to explore how far we can go with. There's something called self-patterning, self-replication. I'm working with some students on a project to do that. Okay, so this makes sense. So the first time I really learned about abstraction layers was back in the 80s. And somebody published a spec for networking. And they said a properly constructed network has these layers, right? So, the physical layer, this is like the electrical signal. This is, how the PHYs talk to each other. This is how maybe the network, there's some protocol about packet transactions. And the fascinating thing was, when you define this properly, you can innovate in one layer without actually having to worry how the other layer works. So prior to that, people would build a new network, and they would sort of say, here's the network packet, protocol, transponder, everything all tied together. But when you did this, you could substitute, make this 10 times faster without touching that, right? And then, so this is a fantastic idea. And it turns up a lot of places. I really like, a friend of mine told me when you build silicon, you only do 4 things. You deposit something, you polish it, make it smooth, you pattern it, and you etch it. And by the way, before planarized metal, they didn't even polish it. You just deposit, deposit, pattern, etch, deposit, pattern, etch. And nowadays, there's a couple extra steps because after you deposit and polish, you might clean something. And then there's might be, when you do patterning, there might be multiple steps for alignment. But it's on the order of 8 steps per layer. And a modern semiconductor process has 60 to 80 layers. 8 times 80 is 600 steps. And if you go in Wikipedia, you'll see for different kinds of layers, there's a lot of modifications to this. But basically it's this repeated process. Makes sense? So so the reason you can make chips isn't because some genius knows how to make an 80-layer chip with atoms placed within nanometers. It's because they've iterated this simple stack with hundreds of thousands of people for about 40 years, right? And that's how we do it. It's cool. So I was looking for who came up with this quote, 'cause I'm pretty sure I heard it somewhere, but it might be me. The complexity is when you have too much stuff in one place, right? And you guys are students, so I remember when I first started to learn like hard math and physics. Like when you first read it, you go, I can't do it, it's too hard, right? But then if it's a good teacher and it's a good curriculum, they break the hard thing down into multiple steps. You learn one step at a time, right? And then you get it to the point where no step is too hard for you to do. And at the end of the course, you go, holy crap, I know what E equal MC squared means. Like it actually happens. It's the same when you climb a mountain. You don't jump to the top, you walk up the mountain one step at a time. Unless you're a crazy person, you climb up the rock or something. But so complexity, transistors give us a huge number. Transistor count gives us a huge opportunity for complexity, but we solve that by abstracting things. And when you're working on a problem, if it's too hard, the layers haven't been done properly, or there's too much stuff in one spot. So here's an example of a computer design stack. And by the way, when we built the VAX 800, we didn't understand this very well. And we had lots of bugs. Right? Well, we thought it was a huge number of bugs. We found 500 bugs in the chip. Today, I was joking with my team that we sometimes have a single RTL designer who can create 500 bugs. But we have tools that are way better at finding them. And people, like, that computer was had 60 gate arrays with 200 gates in each one. So we built a $500,000 VAX computer. So it probably had a megabit of SRAM in it, and these gates were complicated. So it was probably something like 5,000 gates to build a VAX computer that was pipelined and sold for $500,000, right? With 150 people. So I'm going to use this framework to talk about a couple problems. So at the top, you have an application you want to do, like a program, maybe you want to run Linux or Java, or you want to do AI. Then you may have an architecture spec about how to achieve that goal. And then you might write a reference model so you know how it's going to work. Lots of people kind of charge into, they have an idea, and then they want to go do implementation, and then they find out they missed something. So today we do reference models that are very thorough about how it's going to work. Then you build a performance model, so you have idea about why it's fast, but you build a performance model to do that. And then that's when you really can micro-architect carefully each block. And then you build a verification strategy to test each block. It's really important to do that together. And then you go to implementation. Right? And each one of these things is a different set of skills. And then when you guys start to work, you're mostly not going to work on the whole thing. Maybe in your career, you start out doing verification. That's a common entry point. It's a good place, by the way, to start. Then you do implementation, and then maybe you work on a performance model, and then you work with microarchitecture. Typically, architects are more senior people, but I've seen startups where kids right out of college went and architected something and built something great. So there's no obvious path. And then sometimes it's personality type. Like verification people typically really get pissed off when things don't work, right? It's a mindset. They worry nothing works, and they're into it. Implementers are typically very conscientious and careful, right? Architects, I'm mostly an architect. We don't worry about anything. We think, oh yeah, we can do that. Yeah, we're going to build a petaflop chip. Get some guys, we'll figure it out. The verification team says nothing works.
Yeah.
But I've done different pieces. By the way, I've hardly written any RTL. I've written some. I've done schematic. On one of the alpha chips, I drew 20 schematics, transistor level design. I'm pretty good at it. And then my team redrew them to make them testable. So that was pretty funny. I realized the schematics were slowly changing. They'd come, Jim, do you mind if we make this one little edit? Sure, that sounds like good. And then they changed all my schematics. But I've written a lot of code. I've written a lot of performance models. I've written several CAD tools. I've done a fairly large amount of hands-on design. And CAD tools are really interesting because it makes you explore the whole design space. I did a logic simulator, a timing verifier, a design rule checker. And then performance models is another way to explore the design space. And this, underneath this stack, Like each one of these things actually has more layers to it. And just for example, under implementation, there's a synthesize, place, and route, timing verification step, design rule checks. And some of those are, like design rule checks is an entire company with 100 people, and all they do is design rule checks. So we've taken the hard problem, build a fast computer, we've divided it into kind of high level pieces, but under that are more steps. Does that make sense? So I'm going to give a couple examples of IP design, and we'll go CPUs. So it wasn't that many years ago, I worked at a startup, and we built a PCI Express controller, right? And there was a controller and a PHY, and one guy built the controller, one guy did the PHY, and one person did the verification. So we had 3 people, built the whole like Gen 1 or Gen 2 PCI Express controller, and it actually had some features for networking, so you could stream data in on the Ethernet, gigabit Ethernet, stream it out PCI Express directly. And there's some interesting things about how you take a 1500 byte Ethernet packet, chop it up, and then send it out on PCI Express, which has a smaller block size. Right. So we built that and did it. It's pretty simple. Verification was the hard part because we didn't think about it hard enough in the beginning. Today, if you're going to go build PCI Express to go in a server chip, where's Tanuja? Is she here? She worked for me at Intel, and Intel had 5 different groups working on the PCI Express controller, and each group had like 50, 60 people. It was unbelievably complicated. But there's a coherent interface, there's the main I/O controller, there's a huge buffer manager because you're managing many, many streams at high memory latency. Then if you want a reliable thing, there's a link error controller. And then even in the PHY, there's a digital part which does simple digital signal processing, and then there's an analog part that does that. And then you might break this into chunks for verification and have a reference model on top of it. Right? It's unbelievably complicated, but you can still break this down like in a Gen 4 or Gen 5 PCI Express controller with, let's say, server level features. This is the design that's required, and it's tens of millions of transistors, maybe hundreds of millions of transistors. The I/O controller at 100 million transistors has 1,000 times more than the computer used to. And then the genius of this plan is you can go build an SoC, right? So we built a chip at Tesla, and I'll draw you the block diagram that we did, but there's a memory controller, and inside that there's a PHY, a controller, a bus interface, and then there's CPU cluster. Inside that, when I say CPU, we had 12 CPUs. In I/O, we had the PCI Express controller. We bought those things, we put them in the chip, and they worked, right? And under each one of those was a whole team. Right? And we built a chip that drove a car in less than 18 months. And the part we actually designed was the AI engine. And Pete Van had this brilliant idea that people have ever used Cafe. Cafe was a popular AI framework a couple of years ago. And he observed that you wrote your code in Cafe. The output of Cafe is actually a list of instructions of AI operations. So matrix multiply, convolution, ReLU. But the problem people are doing is we're taking that list and then compiling it into a SIMD language, right? And then the compiler to manage that code is really hard and complicated if you want to go fast. But in a car, we knew how big the image was. We knew how much weights we could afford because we're going to keep them on to die. And then we built an execution engine that executed Cafe instructions correctly. But we didn't have to translate that. So we removed a whole set of abstraction layers because we matched Cafe exactly to the hardware. And Pete wrote a compiler for Tesla in half the time. Like, it's an amazing phenomenon. And the chip itself was very complicated. You know, it had billions of transistors. You know, 12 processors, a GPU, and an image processor, DisplayPort, all bunches. But we do that because we really make this modular. At Tensor, when we build an AI chip, there's 100 processors. There's only 6 or 7 different physical blocks at the top level, and they're hooked up with 3 things: knock, clock, and scammed. The top level SoC assembly is super simple. We almost never find bugs at the SoC level because of that structure. So I worked on, I guess, Zen 1, but when I was there, we built a plan to do Zen 1, 2, 3. We actually had a plan to do an ARM process. We were getting a really great plan. We realized if you look at the front decode of the machine, like the I-cache for ARM and x86 is the same, and most of the execution is the same because all modern computers are actually RISC machines inside. And the only block you really have to change is the decoder. So we're looking at building a computer that could do either. Although stupidly canceled that project. Like I said, over the last 40 years, we went from non-pipeline computers to pipeline, to super pipeline, to super scalar, super pipeline, to out-of-order execution. And we went from thousands of gates to hundreds of millions of gates. And probably speeded up the processor about 25 times.
You said that within the ARM and the 6 it was just only the decoder. How the remaining one it actually affects the other part?
Yeah, so we did this funny analysis. So if you look at the floating point between x86 and ARM, they both have like 500 to 1,000 instructions. If you look at the execution, floating point programs really only execute about 20 instructions, depending on data. Load, store, multiply, divide, add, subtract, take, store. So the overlap in the execution space was 95%. The other weird stuff like swizzle instructions and add without carry and flip and clamp and stuff. There's a lot of those instructions, but they don't take very much area. So while the matching of the instruction set was not great, the area overhead was 20.2%. In the memory model, what it turns out, you can always make a memory model strong. ARM has a weak memory model. You can build a computer with a strong write order and then run ARM code on it. And what you'll find is it doesn't run much slower for the wall, but it'll save you a lot of time because of the memory. We picked a memory model that's relatively common. You look in the load store unit, L1, L2, plus interface. It was like more like 1%. Decoders, 100%. I-cache, 2%. Branch predictor, 0. Register renamer. There's extra operands and some ARM instructions. It was an interesting. We designed K-12. Shrikant and Divya work on K-12. They're here. You want to ask them about it. In parallel with Zen, and we thought we would have a common backend like L2, L3 cache, try to solve the combined thing early. And then we did different front ends for the two different chips. And the next generation we were going to finish the merge. That got canned after I left because it sounds really hard, and managers get scared of each other. Like most managers are scared of change and stuff. As I said, I'm an architect, so I'm not scared of stuff. So I worked on this for a long time, which has been really fun. And I just want to talk a little bit about CPU design. And it took us a long time to figure out how to break this problem down. Because, I used to think, figure out what you want to do, you write a performance model, you start writing RTL, and then at some point you hire verification people start doing it. But our modern designs are too complicated. And we're building a new RISC-V processor from scratch. And we've been thinking hard about how to go build that. Right. And at the top, we're going to run Linux, we're going to run vector programs, we're going to run AI programs. There's some scheduling code for scheduling AI to run. There's a bunch of network acceleration. There's some stuff that they call data prep, storage acceleration. So we have a pretty big list of applications. Some are pretty standard. Some of them are very data intensive and high bandwidth. So there's some considerations in a processor design when you say, I know I'm going to stream a lot of data in and out of this and not cache it. Right. So the architecture itself, turns out we want a very high integer spec rate on that. We want fairly big vector units. We want cache coherency because we're going to build a clustering processor sometimes to work on the same problem. we looked at non-coherent stuff, there's some issues there. We want a very large L2 cache, and then L2 cache we can stream data into. So we're doing that. We use RISC-V Whisper model. The guy who supports that works for us. So we put some enhancements in it from some of our changes. And then we also added tracing capability, and we're going to open source that. We're going to open source tracing as well. Because my experience, I've seen a lot of students work on like an architecture project, and they spend all their time getting the traces and a bunch of other stuff, and less time doing experiments like branch prediction or whatever thing they want. So we want to open source some of that, so people will spend more time on that part of it. We built a performance model that's tightly matched both to the reference model. The reference model can spit stuff out on boundaries and to the microarchitecture. We're building this in layers. We actually have different teams. We have an architecture team with a small team. Some of the teams are small, like one person, but. And I would say this is the top level architecture spec. So it's 8 fetch, 64-bit. Got 2 vector units, 2 load store units, 4 integer units, a tightly coupled L1 cache. It's connected to a shared L2 cache. And the status of this is we started it. When did we start the team? Beginning of last year, and then we decided to do something interesting. We have a baby risk in our AI process. We'll talk about self baby risk, so this is really small. And we decided to double the performance of that. So as we hired people, we started working on a small risk project to get up the reference model, the verification tool, a bunch of stuff, and build a vector unit for the 120-bit wide vector unit. And so we did a lot of work on building the team and methodology. And then I guess at the end of last year, we really started working seriously on this one. And now we have a performance model up and running. We have a good part of the mid-core RTL up and running and finding instructions. We have verification environment, but we're still building out the rest of the pieces. So this has been an interesting project. And just a shout out for RISC-V. Yes.
Interesting that point of any point. Wait,
All right, so here's the secret. Here's the secret. Right? Compilers generate basic blocks. Basic block. The average is about 6 instructions. And you typically see like load, add, subtract, pair, branch, store. 1, 2, 3, 4, 5, 6, 7. There's only one. So that's a typical basic block. There's a high variation that could go from 1 instruction to hundreds, but the average is that big. And then these typically get scheduled. The compiler kind of spits this out, and maybe, there's like a load that fed that one. So maybe you could do a little bit of code motion, right? Imagine this is 6, and then an out of order window on a modern computer, 600 instructions. Okay. That's 100 basic blocks. When you get a conditional branch, that breaks the control code. This instruction state, this is an add, it's not dependent on that. Right? If you predict go there, this add can come up. So there's dependencies that the software thinks exist. Some of those dependencies are broken by predictors. Right? The thing we principally predict is the branch flow and the load and store this, because we predict those. So as we make computers faster, so you say, oh, we had 1 wide in order, that was okay. 2 wide in order. So now the compiler has to start to do it, but they can't always pair instructions. At 3 wide, 3 and 4 wide in order was a very good idea in terms of code. And then there was this kind of people working very hard on compiler technology to do something to do. And then we go a 4 wide out of order machine. And the first one did those 20 instructions. But you could see that 20 instructions was only like 3 or 4 basic blocks. But that let us actually started to get some real overlap there. And then when we first did it, we believed our order was so hard to build. Well, it turns out you can segment this and break it into pieces and recalculate. And so the marker architects have been beavering away bigger and bigger. I work on a machine that's, let's say, in the 1,000 instructions. Now, as the window gets bigger, right, if you put 600 instructions, that's 100 basic blocks to fill it up. You can't make a single mistake in 100 branches. Every time you make a branch mistake, you flush out that. Now there's another trick. Sometimes you fill it up. You do a bunch of execution. You branch away from it. You flush it out, but you remember all the results because maybe the program going like this made a mistake. You went over here and you came back. Right? These instructions got executed twice. You save the results. There's all kinds of crazy stuff we could do. But so the prediction is fill the window. As you fill the window, you have plenty of things to do. 8 instructions is small compared to 600. Like it's really interesting.
We're going to be limited in the number of people within the number of outstanding.
As the predictor gets bigger, like I'm telling you, we have predictor technology right now that can fill the 5,000. That's 1,000 basis points. That means you're making one mistake on a branch. It's 99.99.
I guess since one or two then the many of this
Yeah.
typically like many of these type of server workloads are front end.
Yeah, so this chart, so we're gonna have a very large L2 cache, and there's a really good prefetcher on this. So that seems to be a better trade-off. So if we make this bigger, and a whole bunch of like the floating point workloads and stuff, I got small PK. So when you're an architect, you have to look across the applications and go, the server only we go to 256. But for HPC codes and AI codes, it's smaller. And then we make a trade-off between high cache versus L2. And then it turns out the prefetcher. And we think that's a good trade-off. And for almost all these features, when you do performance modeling, you end up with these sensitivity graphs. And they often look like, it's like maybe it's a D in the curve, one kind of graph, where there's a linear relationship, like bigger in caches. Sometimes we see things like this. But once it's big enough, bigger doesn't matter. So as architects, we explore the space of all these features. And then the architects and the implementers have a wrestle about, well, I want to be before the knee of the curve, be after there. This is, pretty expensive. They don't be there. Right? And then we try to make it modular and configurable. And a lot of times, when you start to build it, you kind of go, it's 64K. I talked to this guy in India and he told me that cache is too small. He was right. I'll send you another. It's possible. Yeah, it's one of the things. I think like architecture, I think our data cache is bigger. The machine, the data cache is bigger than the high cache. 128. Right, and we used to make very small data caches because we wanted to use the virtual physical index bits. Like you'd make it with a 4K page, you make 32K with 8-way associativity, so you'd have to translate those bits. We gave up on that. We predict those bits and then cache them. There's probably 15 predictors in this machine. We predict the stretch stream, the alignment, the branches, the calls, the returns, the decode alignment, the load store ordering, the L1 fetching, the L2 fetching. I think I did 10. There's a couple more.
So don't you actually get we also like more technically import more attack surfaces later on?
It's a thing. I'm an architect, I don't worry about stuff like that. So most of the attack surfaces are not in the processor, they're actually in the weird control stuff in the server SoCs. So companies moving out to all these server features, that's where the attacks happen. Like in phones, it would be JTAG combined with the power manager, combined with some frequency widget, combined with a synchronizer. Like I worked on a couple of security hacks that like the weird thing is it's like there's a crack here and a crack there and a crack there, and you can get through the crack. If you can make a script for the crack, it doesn't matter how complicated it is, you can repeat all iPhone hacks. And maybe somewhere like there's this big exploit about you get a program to push random stuff on the stack to get the computer to jump to the next. But that was really easy to fix because you just said the stack's not executable. Once we did that, that whole hack went away. But what they did to do that's amazing. Guys, I want to shout out. So I worked on some open source before, but David and Krista and some really great students made RISC-V happen. They built this thing called a rocket core and a boom core at Berkeley. We've downloaded those and run them. I thought, great, we're going to go find 10 bugs and tell them. And did we find any bugs? Yeah, a couple bugs. Like we have super professional verification people, but they did a really nice job. And then they wrote it in Chisel, which is an abstraction layer of Paralog, which we're very interested in. So that's super cool. And then today, like they're all, I think, in India now, Sci-Fi, Ventana, Rivas, and then Tensor. We're opening up an office. If you want to work and build computers, let us know. This is pretty exciting. And the thing I love about, so we went to license a processor for our AI chip, and we wanted to add some floating point. And like x86 was no go because Intel ain't don't really license. ARM basically said, no, we don't want to subvert the architecture. And Sci-Fi said, sure, put it in the next release. And innovation happens when you have a problem, you can solve it and then keep going. So I think RISC-V is going to go faster and it's going to slowly expand. All right. On the microarchitecture thing, one thing we've decided is we really want to focus on building very well-defined interfaces block by block. So it turns out the pieces of the computers are literally like computers, like the fetch stream, the decoder, the renamer, the scheduler, the execution model. Each one of them actually feels like a computer. They have an instruction interface. They probably have a memory interface. They have a kill interface so we can flush instructions, synchronization interface. We're defining all those pieces. And you would never do this with a small transistor counter. You have the cleverest way to optimize the wires. And now we can say the low store unit has two memory interfaces, and we build a memory interface block and make that super testable. And then the verification team can then say, I know how to test these 10 interfaces. And then we use those on different parts of the computer. We're trying to manage complexity by abstracting this. And here's our microarchitecture pipeline. So it's 14 cycles. One or two places there's an extra cycle because we're building in a future expansion as we add more stuff. 8 by way is not the end. I think after 8 we might be 12 or 16. And then make that happen is partly the programs and partly the predictors to support keeping that pipeline full. But we know how to fetch multiple basic blocks at a time. And if you don't mispredict, that instruction window gets done. Really wild to watch our order machine execute. Because in a given cycle, we might pull out that instruction, that one, right? They go, and that one, and that one, and that one. They go. Fetch in order. It is crazy out of order. 600 instruction window, you have 600 cycles part execution. This is the, let's say, all of them and this time. You might see one instruction hanging out there and like 500 gaps. This is waiting for that one disk of memory to show up. But for what maybe it was an add that went to a branch that was predicted, so it had no dependency. So it just sits there hanging up a scheduler. Then it goes, and then you see the front end orders and stuff. The machine is actually executing very on a caterpillar-like way. One part moving fast, one part moving slow. There's lots of buffering done. So I could do a 4-hour lecture on this one, but basically fetch instructions into a big buffer, align them and decode them. There, map, read the mapper, write the mapper back, dispatch them, pick them in the scheduler. 1, 2, 3 cycles. This is where we're executing. Yeah. Right. So here's the modern, never the, fetch, decode, register, read, execute. Cycle 4. Or it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Cycle 14, the execution instruction. 10 cycles of overhead, but the mispredicted rate is still low. Those pipeline stages are great. Yeah. So this is the modern computer architecture we're building from scratch. Okay. So our innovation is provable interfaces, scalable definitions. We're looking at making some of this modular, so you could say, hey, I want to build 6 wide or 8 wide, 1 vector unit, 2 vector units. We're trying to build load store units as things that we could replicate more in the future. There's a lot of interesting things to do. We think there's going to be new data types for AI. We've already invented some data types and put them in. There's a lot of research going on in that area. And then we're building this partly because it's fun and it's valuable, but partly because the AI computer and the regular computer are working together. And we think having that connectivity, be it say hundreds of nanoseconds instead of hundreds of milliseconds. Interesting. And the other thing is when you do a new project like this, there's so much to learn. And I think the next 10 years of innovation is going to be interesting. And I'll circle back to the craziest one we figured out. Okay. So here's another way to look at Moore's law. Right? Way back when we had hardly any transistors, we had non-pipeline computers. Then we got enough to pipeline them. And then we got enough to do out of order. So I built an out of order computer in 1995 called IISc. Right. And it was a scary big number of transistors. It was 4 wide, out of order, 300 square millimeters in the 0.35 micron technology. That would be a fraction of a millimeter. And that took 200 people like 3 years to build. Right. And then at some point, GPUs were coming along, and GPUs got enough transistors to actually become programmable, so they become shaders. And around the same time, we started to build multi-core. And when we built K8 for the first time, we built the architecture bus hypertransport. And I told people we're going to put 4 processors on a die. Start with 1 and then 4. Everybody said that's crazy. Nobody will ever put multiple processors on a die. It's too much power. The transistors are too expensive. Would you rather have 1 big faster processor than 4 slower ones? A whole bunch of reasons. And now we're talking about like our processor at 4 nanometers, 1 square millimeter. That's overhead, but we might put 100 of it. 54, 100, 256, maybe. We can do that. It's amazing. But so AI took way more time. So Jeff Dean had a pretty good talk at back a year or so ago. He's the CTO, I guess, at Google. He said there was a time when they were getting this AI program to kind of work, and they were trying to scale it from 1 to 64 processors. And they spent all this time to get the 64 like regular CPUs, and they realized that was 1,000,000 times too slow. The algorithms work, but the computation to get something interesting. But 1 to 64 didn't help. They needed 1,000,000. Right. And the reason AI is starting to happen now is partly innovation like AutoGrad, model like Inception, ResNet. The AlexNet was the famous one that was for the first time beat computer vision. But the transistor count to do this is intense. And then, there's a joke. I like this joke. So we made the slide when we were raising money. We quoted Andre Carpathy. Andre said, for 40, 50 years, software 1.0 is you wrote programs, right? And they kind of look like that voice in your head where you said, do this, and then this, and then this. And then software 2.0 is you take large amounts of data and you train an AI network to do something. And there is no declarative sentence. And the joke part is, you're going to quote somebody, quote Andre, to me, raised $200 million. Well, that's pretty good. And then the ironic part is Andre writes a lot of code. Like he said, in contrast, software 2.0 can be read more abstract, human-unfriendly language, such as the weights, and no human is involved in writing this code. Well, he quotes 10 hours a day, so I don't know how that works, but the fact is, the actual AI programs are small. But the code they're writing is testing, optimizing, convergence, but the actual CNNs are, there are literally hundreds of lines of code. And then I'm a computer architect, not an AI architect, so I've been reading lots of papers. I read a couple of papers a week. And I slowly realized that, you know, the AI guys write programs like this. Has anybody read or written an AI paper? Right? You know, you have to put some math in it. Come on, let's see some hands. You've seen these things, right? And I realized I don't know what that means, or that means, or that means. I don't know what that means, or that, or that. Looks like that. So it's two of those, but it's actually indexed with a different thing. And then it says 4, and I don't know why that's there either. I don't know what any of that means, but I'm a computer architect. I know how this executes. It all turns into this. A equals B times C plus D. Like, I'm not kidding. Like, we built a computer. We know what's in. Add, subtract, multiply, divide. Now there's a couple of other accelerated ops, and we use these in HPC as well. 1 over x squared, 1 over the square root of x. Min, max, clamp. There's a bunch of dirty, like if you use floating point, you know that rounding modes and error accumulation is the real problem. And AI is weird because on the one hand, it's relatively insensitive for precision. There's places where you actually accumulate tens of thousands of numbers. And if you have a small error on a 16-bit float over 10,000 apps, it'll kill your accuracy. So there's a really interesting phenomena that happened in this. So this stuff, and by the way, I'm sure the people who write these papers know what they mean, and they're using some of this math because in the way the data, the models are trained and how the data is related to that math is actually important. But in terms of executing the program, we've abstracted it to a whole different kind of thing. And then the programs are small, hundreds of lines of code. Like the transformer is 300 lines of code, and it runs for a month on 10,000 GPUs. Right, that's a lot of time per instruction. And then the real thing is, these programs, the way we do it, don't execute as programs. They actually build graph, and then we do something. And here's an example of graphs. So we've taken all the random codes, and you can see it. You know, you go to Hugging Face or GitHub. You know, BERT transformers, CNN, ResNet, RevNet, RLMs, DNNs, right? And the diversity graphs is high, right? Like here's a straightforward graph. Do something, and do the next thing, and do the next thing. Here's an interesting one because there's a path where the graph is going piece to piece, but there's a path where you're forwarding data. This one has a zigzag pattern. This one has a merging pattern. This one's got circles in it. This one is random. Sometimes I think what happens, college students are looking for something to do, and they think, well, I don't see this pattern. Let's see if that's an AI network. Is that what happens? Everybody's giggling. It's nervous laughter. That's what they're doing. They're your students. It's not my fault. All right, so here's the funny thing. There's only about 5 operations in an AI program. So there's thousands of people working on this. The math guys think they're doing differential equations and power series, and exponential sigmoids, transcendentals, stuff. But we know how to compile virtually all that math in the matrix multiplies or convolutions. Turns out there's the transformations. We turn convolutions into matrix multiplies. So our first chip has a convolution unit, but we save some transistors when we figured out how to do that. ReLU is basically a threshold detector. Softmax is the way to prioritize numbers and then get more than one of them. That's why they say soft instead of max. Attention is a way to take an input string and relate it to each other, and it's a dot product on a matrix multiply. But like I looked at the math for it and I thought that's got to turn into a matrix multiply, but nobody's done it yet. And then generically tensor modifications means take data in one vector matrix format and put it in different, possibly, inverting it, transposing it, doing the determinant, changing the precision, bloating it, shrinking it, 2D to 3D convert, you name it, we've seen it. But it's generically just move data around. All right, so you'd think 5 operations, how hard could it be? That's subtract, multiply, divide, data around. The program itself is 30 lines of code. It's 50 AI startups, virtually nobody's cracked this problem properly. We think we're on the way to doing it. But the generic thing is basically architects, mostly hardware people, say AI is all about flops. So they make a chip packed with small ad units, right? And then they hand code ResNet. They get this really good number, and then they quote Andre Karpathy and they raise $200 million. Right? And then the next thing is you make a compiler that compiles many things, but the performance is very variable. Somebody makes a new graph with some subtle tweak and it all breaks. And we did that. And then from there's 2 things. One is you try to solve the problem, which we're trying to do. The other is you hire hundreds of people for every customer and hand code their code. And then your theory is at some point somebody will ask for the same thing you already did, hand code it. And NVIDIA has several thousand people doing this, and it's turned into a successful business, right? But if you just write a matrix multiply in CUDA, naively, you'll get 5% of peak performance, right? And then there's some HPC transformations like blocking and caching, and you can get 30 to 40%. But to get 80, 90% of peak performance, you got to know where the register files are, exactly how SIMDs work, exactly the size of the on-chip memory. And they call them CUDA because they're really good programmers and it's really hard. So all the high performance AI stuff has had somebody at that level look at all of it. All right. So we've rewritten our software stack 5 times because we're actually trying to solve this problem. So our new software stack is starting to work. And last year we just took a step back and said, let's go look at the stack from top to bottom. So the applications are clear. PyTorch, TensorFlow, data prep, data optimization. We know that we're going to go build this in big arrays of computers. So Tanuja's here, she started building a cloud computer. We have 1,000 of our chips on the cloud, distributed across servers, high performance network, high performance servers, storage servers, OpenStack. There's a whole bunch of work to do on that. We had good reference models. We built a new performance model. We started thinking about how does the architecture verification stack. And then we started mapping this properly. So at the top level, what we see is the applications. The programmers in the outside world worry about data prep and stuff. But we consume TensorFlow and PyTorch, and then there's this program called PDM, which translates that to an internal intermediate representation that turns out we like, right? And then we do a graphic expansion in the language we call Buddha, related to Buddha. And that's our internal graph representation that contains matrix multiply, tensor transformations, all those things, right? And then we do a graph transformation on that for training. So AutoGrad is a graph transformation. And what goes into our stack at the bottom doesn't care if it's inference or training. And it turned out there's some really cool models that actually are using inference, but they use the AutoGrad method.
Because when you take a model, you compute forward to get the answer. Autographs, you compute backwards, distributed way. That makes the AI model reversible. You can put an image in one side and get cat out the other side. On the back pass, you can put cat in there and get the cat back out. It's really cool. Right, but so there's a generality of those graph transformations. Then we have a graph lowering step and buffer insertion step, which makes big matrix multiply pieces that fit on our AI processors. Right? And then we actually do something, because we're computer guys, we place and route the pieces of the subgraph across an array of AI processors. Then we compile the low-level kernels, because some people go tweak like transcendentals, exponentials, like the usual matrix multiply determinant inversions are all written. But you can go right in kernels. And then there's a data flow compile that stitches the pipes between all of computation up. And then underneath that protected run. And then we have a simulator, so with every major level we can simulate this. And then our plan is, once we get this work, we're going to open source it, so people like you could write a program and then go play with it at different levels, which is really cool. Everyone heard who's Satya, the Microsoft CEO? He called me. Like, it's like one of those, hello, Satya. Yeah. We had a funny conversation, because he said a lot of AI startups believe the software stack is their secret sauce, so they keep it secret, encrypted. And I had that experience at Tesla trying to get good performance out of GPUs from everybody. Because you write your code, you get bad answers, you get wrong answers, you get stack stumps. And if it's an encrypted binary, you can't be like it. He said Microsoft is a programming company. We don't have access to program the AI. So after talking to him and a few other people, we thought, well, we're a hardware company selling this stuff. We have a software stack to enable it.
But we want to really let people go play with it. And my prediction is the people start looking at it are going to call us up and go, Jim, this is really stupid. Here's a way better way to do it. And the open source world is really great at accelerating innovation. We'll let you know if that happens, or they just steal all our stuff. Like maybe it's a dumb idea, but remember, I told you we raised $200 million, so we're going to spend it anyway. So here's a piece of BERT, which is just, query key value dropout. Like if you go look at the high level models, these are the standard things, right? And then we turn that into a graph. This is literally a fully connected layer. We multiply, element wise add, probably reload, fully connected layer, softmax. And those routines can vary from 10 by 10 to 10,000 by 10,000. Right? And our AI processors, little p, forensic whatever we call it, our AI processor, about a megabyte and a half of memory, it's a megabyte for data, and the other half a megabyte is input buffers, output buffers. So if you have a matrix multiply, that means 8 megabytes of memory, 1, 2, 3, 4, 5, 6, 7, 8. Okay. We take the graph and we place it piece by piece. So when a GPU runs it, this program, it fills the GPU with this and runs it. It fills it with this and runs it. So it runs it sequentially. If you write the Verilog program for a RISC-V processor, maybe some of you have done that for like a simple pipeline. The Verilog program, when you run it, runs the first stage, the next stage, you run it in order. When I did performance models, I always ran the pipeline backwards, because that gave you a master-slave effect from the order. But when you build a computer, a pipeline computer, all the stages execute in parallel every time. Right. So when you hit the clock, decode starts decoding, renaming starts renaming, scheduling starts scheduling. Right. So that's a parallel execution model. Now it's pipeline parallels. So when we take this model, we say, run this, run that, and we give each operation the number of cores it takes to do. Right. And then it runs like a pipeline computer. So if you're doing training, right, you're going to put into this 1 trillion data sets. So the first time this guy runs, these are all empty, like just filling up the pipe. Then the next clock, this goes there, and the next one happens. The next clock, the next one happens.
And pretty soon what you see is, so these big transformer models, 1,000 pipe stages deep. Takes 1,000 training elements to get the pipeline. Right? But once the pipeline's full, 1,000 piece of 1,000 different operations are happening in parallel. And this is one of our innovations is, it's not art, like people have been doing data flow for years. Because this knows how big it is and it knows where that is, we send the data to there. For a GPU, you run this, you read the operands from memory. HBM, expensive high-speed memory. When you're done, you write it back. Because the code doesn't know what this is doing. It's not a graph analyzer. So we use way less memory analysis. We try to flow the data. So the weights for this matrix multiplier are actually distributed across this processor and stay on chip. And the activation flow it out the pipeline. Now here's the really funny thing. So I told you, AutoGrad is a graph transformation with two different graphs. One of the features of training is, I did a calculation here, which may or may not be right. So training saves and holds it and waits for you to go all the way down the pipe, and then all the way back, and then compare what you calculated versus what the updated error model says you should do, and then adjust the weights.
The reason I asked that pipeline is different.
Yeah, but just think about, to us, it's generically a graph. It has computational elements and data buffer elements. We can buffer stuff with 1,000 pipes. Like for an object, we have local DRAM. So when you're doing training, these buffers start to pile up and then we move them off chip to DRAM. And then when they come back, we time it so that we pull the buffers back on chip just in time for the back pass to hit. And then there's another trick, which is, it's called, we regenerate. So if we do this and this and this and this forward, we don't have to save all the emitter results. Because we can say like, that's a small one, and then regenerate these three. Right, because it's less work to recompute the forward pass. The way we generate the forward pass, there's a backward pass, there's a recompute pass. And then we save a minimal amount of data. And the graphs for inference and training are very different, but the stuff that lays around is completely generic. Question in the back?
So, I mean, enter this fast P here, because these days the model are very sparse, right?
Yes.
It's fast P and
Yeah, so we have a very long talk about that. But here's the really cool thing. If this is a really big matrix multiply, right? We generically process things in 32 by 32 chunks. You can say only execute half of the operations. So then we have a little bit of code we throw in there that looks at a 32 by 32 chunk and predicts whether or not this will have much, like say the chunk is all zeros. Don't calculate it because you don't know what the answer is. Now, because this is a pipeline problem, we want the pipe stages to have about the same compute. So if one thing was like almost all zeros and the next one was almost all full, it would be unbalanced. We have some software to handle that.
the competition part, right? The other part would be accessing from the memory, right? Which would be more.
Yeah, so when the pipeline, like for something like ResNet or BERT is running, the weights are almost all on chip. The data inferences are flowing through the chip. We're never waiting for DRAM. That's not a GPU. Right? And then we can do dynamic, so you can do structural sparsity where you do analysis at the high level about the weights and compact the graphs. And then there's dynamic sparsity, which you say, in this model at this current moment, you can do less calculations.
In the concept.
Yes.
It's difficult to find in these days.
Yeah, so graph processors are particularly good at this and GPUs are particularly bad. We've had some Q&A sections where half the people are from NVIDIA asking us how we do sparsity because it's very difficult to program on a GPU.
Another question, but we enter the quantization, right? But most of the time you do the precision, right?
Yeah, so we support 4-bit, 8-bit, 16-bit, float and block float, TF32, 32-bit, and then,
Well, let me just talk about the hardware a little bit, and I'll give you some examples. So we build an AI processor. So we have a chip. There's a PCI Express controller, a DVR controller, Ethernet controller, an AI processor, and a bunch of NUCs that hook it all together. And generically, the AI processor has some little baby RISC processors in it, some math units. There's a big 32 by 32 matrix unit, a big vector unit. There's data formatters, there's local memory, there's a data mover, plus some things. All right, so these are the microarchitectural components of the processor. And then it's sort of, this is a little abstract and I left out like one big secret, but basically there's 5 RISC-V processors. One of them talks to the bus to coordinate data movement. 2 of them talk to the input data formatter and the output data formatter. We call that the unpacker and the packer. And in there, we can actually, say you have the data like in 16-bit format, we want to calculate it in the 8-bit format or calculate it in a 32-bit format. So we generically reformat the data on the way in and out of the matrix units, and then put it back in whatever format you want. And these both have some extra stuff that for a lot of the simple tensor modifications, as the data flows through this thing, we can do squiggles of matrix and blow-ups and shrinks and a bunch of operations. And we also detect dynamic sparsity as the data flows through. And you can say, instead of taking this long operation, like a 32 by 32 matrix multiplier, when you're doing a lot of these, it takes a lot of cycles. Right? And then we can say, oh, these blocks aren't good, and we can truncate, use dynamic sparsity and get rid of a lot of operations. And then there's a whole bunch of stuff that watches the precision. So sometimes you just run it, sometimes there's some interesting stuff about, like, you might have to do normalization, or you might have to, as you're debugging your thing, shift, say these 2 layers have to change the precision to avoid precision problems. So there's a bunch of tricks in there. And then there's some additional math, and I'm not the expert on how we do some of the exponential softmax and other things, but there's a whole bunch of math tricks. Does that make sense? So this is generically an AI processor, and this bus interface is actually hooked up in a mesh, so there's 4 parts coming out of it. I talked with RISC processors. So generically, when we make an AI chip, there's this NOC. And by the way, Bill Dally, professor now CTO, I think at NVIDIA, wrote a book on non-blocking NOCs. So we read his book and we built that NOC, basically, the non-blocking generic packet NOC. So it's a nice open source project. So the AI processors talk with the NOC. So imagine these 2 processors are collaborating on a matrix multiply. They both have half the data. They actually send each other the data because for an n by n matrix, you do n cubed computations. These things are generally speaking. So we made the memories big enough to hold interesting chunks of data, but small enough that you're not dragging data across a very large SRAM, which wastes power. So we think, you look at the size of an AI processor, there's a sweet spot for power efficiency. Too big and you waste power on SRAM. Too small, you waste power because you're having to send data around too much because then 2 over squared. Right. And then the other thing is we want to balance the pipeline. Right. So you take a big matrix multiply that takes 16 cores and a small one takes 2. Having the ability to really scale the compute means we can balance the cycles of all the different places. Like a GPU sort of has 2 big matrix multipliers. So if you want 1.5, you have to waste those. And then turns out on some of the big models, matrix multiply is so big, taking multiple chips. But that's okay. We don't care. That works fine. And then the SoC itself, there's a PCI Express block, memory controller block. Our 2nd generation part has 1600 gigabit Ethernet ports. And by the way, so if this processor wants to block the processor on the other chip, it gets up to this controller, and the front of this controller just takes that AI data packet, encapsulates it as a layer 2 network packet,
sends it to the chip it wants to go to, which uncapsulates it and then just sends it on top. There's no driver, there's no, but we scale out lots of chips without actually running through a network. That's one of our interesting things. Our compile sees arrays of tensor cores and DRAM, and it thinks about like the local memory here is low weight, that's higher weight, that's higher weight, that's higher weight. Memory over on that chip is higher weight, but it's just a weight problem. So when the places it routes it, it figures that out.
All right, I'm almost done here. And we're building the next gen now, so
It says 4, but our next chip is 6 nanometer. We're going from like 100 to 250 AI processors. First generation, we licensed Sci-Fi RISC-V core, still issue in order 2 vector units in next process. And then our team is building 8Y algorithms for the next generation chip. And one of the things we're going to do is you can have AI calculation in a graph, send data to a processor in the graph, do a more complicated operation, send it back real time in the graph. These can also be used for network acceleration, data preparation. It's pretty cool
processor. And then,
so we're building, we have this convention, so we're building AI computers. And you know, for 50 years, computers ran C programs. Now AI computers, we train weights. There's a huge line. They're not anything like. Well, you can emulate an AI computer on a GPU or a CPU. But we're building AI computers that are designed to run AI, like heavy math. And the cool thing is the OpenAI guys, they work on GitHub Pilot and Codex. And there's a really funny video of them, like real time using AI to write a game engine. And a couple of our guys tried it to write a test bench, and they said it was ridiculously easy to generate code. So we're starting to think about what's the world going to look like when, you know, instead of writing a low-level C code, you write the instructions to AI to make the code. And here's one of the really interesting things about building both AI processors and this slide. Talks to some architecture friends, and humans writing the serial narrative, but AI is really good at an all-to-all relationship. It can track a lot of things in parallel. You think when you start to write code with AI, the first versions of it are trained to write code like humans do. But they're going to start to write code like AI things in parallel. So those binary programs have been massively parallel that change when you build CPUs. Because CPUs do what you tell them to. AI calculates weights and does what it wants. Right? So there will always be a place for both kinds of things, but the architecture generated by programs written by AI is going to be very different. I'm predicting in the next 5 to 10 years a 10x speed up. They asked about how fast can it go? So today, a shipping processor runs 3 to 5 instructions a second. I work on a computer with 12 instructions a cycle, 12 issue, sustain, execution, and I think we're going to get to 100, which is a long way from 0.1. So here's a picture of our computer. Today, the first gen is PCI Express, sort of 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 cards in there. There's 2 chips on each one. So it looks sort of like a fat tree of 8 AI processors that can all talk to each other on PCI Express switch. And then there's 2 AMD processors that can do data prep and management and talk to the cloud. Fusion, the team built, we have a colo, we have 1 megawatt now data center. We built probably 100 servers, we have about 2,000 chips deployed. And we're bringing like small, like 1 chip models up to hundreds of chip models. And then our next generation, like you can see, this is a 4U server, it's about this thick. We built our own 4U backplane and we get 32 chips in that, fully connected with Ethernet. And we're building a machine with 1,000 processors. It's a 32 by 32 array. And an AI programmer should be able to write an AI program and compile it and deploy it to that without having to write nickel or Knox or MIPI or. It's really an interesting proposal. Right.
Any questions?
Basically a grade of respect. You mentioned that you have a grid of respect process.
Yeah.
So how important is outer order? They are relatively low on.
Yeah, so here's the interesting, so each one of these guys has 5 baby risks. In our next generation, one of them has our vector unit. So most of the math in there, but those processors, when they execute an AI program, it says, get some data, do a math operation, do a vector operation, push some data. Like you're right, and they chew up the instructions and they sit there waiting for the math to happen. So these are in order, super small baby computers. These guys over here, they might be running Linux, they might be running a search, they might be doing network processing, like they might have a big gobbledygook floating point program that somebody really wants to do, right? So we built these to be both servicing the I/O, talk to the world, right? But they also, say you write this graph and then you have a secret, like maybe just doing some development, you want to experiment, right? And you want to write a fast C program and say run it on 10 processors, right? Having these these out of order cores here, means that layer will go fast enough that your experiment can work. And then you might say, this is a good idea, I'm going to move that back into AI. Or so what we want to do is make the new platform be diverse. Does that make sense? So and this is a really cool thing about RISC-V today. So we have a baby in order 1 issue guy. We're using the dual issue here. The next gen tree was speculating with the guys that we might want a higher diversity of issue rates in here. So we might have like 3 baby risks and 1 dual issue risk and 1 out of order. So we can have different instruction rates for different parts of the screen and still be like maximally efficient for each one. And then on the edge, we'll have the big guys that can, keep up with the big boys for C programs. So it's interesting. Any more questions?
So you mentioned about there are more clock to put in more transistors.
Yeah.
But how did you come to that conclusion that clock would be the bottleneck in the sense, or why not something else?
Yeah. So this is a really good question. So this is what architects do, or they're supposed to do. We started looking. You started with the problem statement. We want to make AI go as fast as possible, right? And then we would like it also to be programmable as possible, not mysterious. It's really like some computers are fragile. Like you write a program and it goes okay, you make a little tweak, the performance cuts in half, or like you went slightly, you made the data structure bigger, it suddenly doesn't fit in the cache, now it's running out of memory. And so there's just a subtle problem here. So that's one dimension. The other one is, like I said, if you make the AI processor too big, it's power inefficient because of the SRAM. If you make it too small, it's power inefficient because of the bandwidth. We have lots of debates about how much bandwidth between cores, right? And then from a predictability point of view, having too much bandwidth and slightly too much memory meant that when you build your graph, when we get to this stage where we lower the graph, we can literally count up the clock cycles of all the math operations and predict how fast that graph is going to go, right? That's a very nice place to be. Because on the roofline model, you're on the compute limited line. That makes sense? And then if you don't get that number, then it's like, well, what happened? Was there a weird data pattern, the compiler made a mistake? For 90% of the stuff we see, we're compute limited. And then it turns out compute is also the easiest thing to build with transistors. There's 2 things that are easy to build with transistors: multi units and SRAM. Right? And if we make the SRAM too big, then we have a worse power problem. So we basically slightly over-indexed on compute. Right?
And that's, and then, to be honest, now we're running a bunch of stuff and we're thinking about what to do next. Yeah, because well, CPUs are generally speaking designed to run C programs, JavaScript and a few other things. So it's easy to put extra flops in them. If you look at a processor, they look at like a high-end CPU. So there's the floating point unit. And you can put twice as much in for a small percentage overhead. But if the memory bandwidth didn't change, only some programs take advantage of that. So it's easy to claim IP flops, but not deliver. But our design is really well balanced. So we essentially have probably have 50% more data bandwidth than flops. So that means almost everything's swapped.
When you are designing the processor, so are you trying to optimize more for the inference or more for trading? Or second question is like, should there be two different hardware, one for the trading, one for the and one for the inference?
Yeah, so our realization was we only saw about a 10% advantage to do an inference only part. Because for the big inference models like GPT-3 and a really big ResNet, they take multiple chips. They spread. So when we compile a ResNet for inference, some of the matrix multiplies take that many cores. And then some layers take a small number of cores, and sometimes you see something that's just a line of cores. Right? So there's nothing at the microarchitectural level that's different. And the graph compiler doesn't compare all of its inference or training. The thing you see in inference is more focused on lower precision. So there's some overhead because we support TF32 and 32-bit floats that inference mostly doesn't use. But even the inference guys, they love to have a high precision floating point because when they're developing it and something's not converging, the safe thing is to back off all the floating point formats, get it to work, and then you slowly whittle down. And then having the same software stack for inference training. Like at Tesla, we had to train on GPUs, but then we had to run it on our home built AI engine. And then sometimes the inference would work on the GPU and it'd fail on the AI engine. And then now you have different software stack, different execution model, different. So there's always like where's the problem? Right. So by having a chip that does both, it's like, so if you want to do primarily inference, but you train on this thing, going from inference to training is really easy. And you can even start the inference at the same floating point performance, and then you can tweak it down layer by layer for the floating point. And that's really cool. And even on training, we have some people experimenting with 4 and 8-bit floating point in training. But it turns out some layers are doing massive accumulations, so they like more precision, but some layers are really light, and they work just fine with full precision. That's a good question. Couple more questions?
If like this, how would this be like standard compiler like operator and other things? Those operator vision like make it fun. This sort of processor is this specifically make the data to that or
Yeah, some of the question is, how do we do operator fusion and stuff? So some of those fusions are done pretty high in graph, right? And some of them actually do them at the TVM level, and then it's generic, that's we don't even care. Right, then there's others where you have the math operation and the tensor modification, and our compiler looks at how to, and sometimes you'll see 5 tensor modifications stacked together. And this is where, like, we can look at the data link of a given piece of data, how it goes through, and then figure out which ones to collapse together. And because we have the graph analysis, we're pretty good at it. So we eliminate, like a lot of times you'll see a big matrix multiplied. So typically what happens, what sets the clock rate is the matrix multiplies. So you lay out the matrix multiplies, and then the tensor modifications hide under a lot of the matrix multiplied. As like it looks
But you know how matrix multiply works. You know, you got two matrices, say, take that row times that column to make that piece of data, right? Then, once you get this whole row calculated, put the tensor modification there. It merges on the row count, the row or column calculation, depending on which way that tensor modification is going. And say you did, you did the last column, this tensor modification, and then you did a shrink where you took two things into one thing, right? We can line those up really well. And then, so, and if this was packed in a processor, now it's packed in a processor, and in fact, when you go to the next thing, maybe it's a smaller number of processors. Our data movers handle that. So where the GPU, all of that would be lots of code. Our graph analyzer says, I got the row, I know where to put the tensor modification, I know where I put the shrink or the blow. Then in the data mover, I know how to set the data up. So you're writing into, you can have multiple processors writing into 132 block, and then the whole block shows up. We process it into the next stage. So this is where some of the compile to get good performance happens, because some of that manipulation is in the compiler.
So if this thing like that, then like the GPU to the it is one waiting for the thing to get dependent. So basically need to try to the memory and again performance reaching.
And so if you have enough chips to fit it, this again, so say you have a really big model and you compile it, so they want 800 chips. For your student, you only have one chip. We have a mode where it will run more like a GPU. It'll do a piece of chip and memory, and like we can run that. But like a really high performance, like ResNet, high precision, runs on something like 6 chips. And then that's full pipeline and it runs screaming fast and it doesn't write memory at all. Like actually ResNet's so fast, it's feeding into the model. Like that's why we like the big memories, because the computation goes up faster than the medium size. And then GPT-3 is really crazy because the way it lays out, it looks like a snake. It goes this way and then turns and goes this way and then turns and goes this way. And it does that through 100 chips. And you can see in the computation, there's a lane for compute and reverse compute and regen. So it's a, these graphs have really interesting behaviors in play now. But it's kind of like laying out a chip. Like if you write the code, it looks one way, your block diagram is one way, but then you go look at where the gates are when you place them out. Like you see, like they got stretched over here because this is talking to this and this is talking to this. Pieces that don't talk to each other, there's one wire that makes them get pulled together. It's a placement.
Earlier in the talk, you referred to an example of executing cafe operators directly onto the hardware without converting them into the system. Is that something you plan to do here as well?
No. Yeah, so what happens is, so Cafe was really good for the initial inference models. The AI programmers have gotten into a lot more variety on both math and the data buffering. When you start looking at these graphs, there are places like this says forward data, a couple stages. Well, how about forward at 1,000? And there's a cool, it's not on here, UNet. It's a very long pipeline of computation, but they kind of roll it up and they forward data into a whole bunch of things. It turns out there's a lot more sophistication on those models for how to do that data buffering, and then how to do what the other question said of how do you take the computation and the tensor modifications and put them together. So far we don't see an obvious path that can do that. So it's all that combinational, like I said, 5 operators, a couple of tensor modifications, huge number of graphs, huge variety of data size, number of processors required. That's caused us to build sophistication into the graph map.
Close to 50% now. I thank Jim for an Okay. Great. Right.
Please coffee and snack will arrange downstairs in the cafe garden. Jim will also be there if you want to have a quick interaction.
And then I think I would have pulled back t-shirt, but
Yeah.
took on it.
Thank you.
They were with us. Hey, thanks for coming, everybody.